Hi, my name is Dr. Ahmath. Welcome back to the video lectures about the integration techniques. In this video lecture, we are going to discuss about the integration by parts. So we are going to try to answer to the two questions. First, when we need to use the integration by parts, and second is how we need to use the integration by parts. So the second question is usually easier. So if you know that you need to use the integration by parts, you probably can do the integration by parts. The main question is when you need to use the integration by parts. So let's try to see when we need to do this. And in order to give you some motivation or in order to give you some insights about the integration by parts, I would like to start with this problem. So let's assume that I would like to find the derivative of this function. And if you remember, in order to find the derivative of this function, you need to take the derivative of the x first of all, which is 1, and then multiply this to the cosine of x, plus the x times the derivative of the cosine of x, which is the minus sine of x. And if you remember, we call this method as the multiplication rule or the product rule, right? So we take the derivative of the first function multiplied to the second plus the first function multiplied to the derivative of the second function. So in general, if you've got your function which is written as the multiplication of the two functions, then if you need to find the derivative of the multiplication of the two functions, then you are going to use this formula, right? So the g prime of x times the h of x plus g of x times the h prime of x. So now we know how to take the derivative of the multiplication of the two functions. Is it possible to find the integration of the multiplication of the two functions? Well, it appears we are going to use so-called integration by parts method when you are given the multiplication of the two functions and you need to get rid of one of them. Okay, so this is going to be our motivation, and you need to always memorize this. So if I can get rid of one of the functions in my multiplication of the two functions inside my integration, then just go ahead and use the integration by parts. So let's do this method. So now I'm just going to, so integration by parts actually is coming from the product rule when we take the derivatives. So we've got this formula that g times the h of x, its derivative, is equal to the g prime of x times the h of x plus g of x times the h prime of x. If you're going to take the integration from all of the three parts, then you're going to get this kind of equation. Please note that on the left-hand side, you are simply going to get simply g of x times the h of x, because this integration is going to cancel with this derivative. Well, if I say that this is the integration by parts, would you believe that? And actually, yes, this is the integration by parts, but written slightly in a different form. So if we are going to just make the small substitution like a u to be equal to the g of x, what is going to be du? The du means that I'm just taking the derivative from the left-hand side with respect to the u. And if you take the derivative from the right-hand side part with respect to the x, it is going to be g prime of x dx. Then the v is going to be equal to the h of x. dv is going to be the derivative of this whole equation. And the derivative of the h with respect to the x is going to be h prime of x dx. So now you see, so you've got here simply u times the v, right? Because derivative is going to cancel with the integration. Here you've got the integration of the v du, plus here you've got the integration of the u dv, right? Because h prime of x times the dx is dv, g of x is the u. So this is u, this is dv, this is du, this is v, this is v. Right? And now if you're just going to put the different terms into the different parts of the equation, you're going to get exactly the integration by parts. And actually the integration by parts, it appears, is coming from the product rule when you take the derivative of the product of the two functions. So I'm just going to make all of the substitutions here. Say one more time. And if you're just going to put this in this way, you're going to get the integration by parts. Again, if you've got the function inside your integration, which is written as the u dv, it can be integrated as the uv minus v du. The main question is again, so why or when you need to use the integration by parts? The answer is, if you've got the two functions inside your integration, the multiplication of the two functions, and if you can get rid of one of them, then just use the integration by parts. If you want to get rid of one of the functions, then use the integration by parts. So let me show what I wanted to say here. So here I've got the two functions, the multiplication of the two functions inside my integration. So I can probably try to integrate x or cosine of x separately, and I think I can do this. I can do the integration of the x separately. I can do the integration of the cosine of x separately as well. But if you've got the multiplication, then it is becoming really difficult. The integration by parts helps us to get rid of one of the functions. So in this case, I'm going to get rid of the x. So I'm just going to make the notation. So the u is going to be equal to the x. Then the rest of the function, essentially dv, is going to be denoted as the cosine of x dx. Okay, so this you see, so you've got u dv. So you see, so on the right hand side part of this equation of the integration by parts, you need v and du. Okay, so if you're given u to be equal to the x, then du is going to be derivative of the x, which is 1, times the dx. It is going to be simply dx. And if you're given dv, you can find a v from here, right? What is going to be the v? So what is going to be the antiderivative of the cosine? Actually, this is sine of x. And the reason is because if you take the derivative of the sine of x, you're going to get the cosine of x times the dx. Okay, so now you've got all of the ingredients of this method, and you can just substitute everything into this formula and find integration. So let's try to do this. It is going to be, so the integration, so this is u times the dv is equal to the uv, so in this case it is x times the sine of x, minus the v du. Right? In this case, the integration of the sine of x times the dx. Okay? So you see, so it becomes easier. So you see, so that inside your integration, the x disappeared. So we basically get rid of this x. Again, so if you want to get rid of one of the functions, then use the integration by parts. So then the answer is becoming really straightforward. It is becoming, so x times the sine of x, and the antiderivative of the sine of x is minus cosine of x. Then with this minus, it becomes plus cosine of x plus the c. Okay, so this is again how we can use the integration by parts. The question is, like, these two questions are always important. So which method you need to use in order to find the integration, and if you decide to use one of them, for example, the integration by parts, how to use this method. So let's do one more exercise. So let's say you are given another function like a ln of x, how we can find its antiderivative. So at the first glance, you might say to me, hey, so I don't have two functions here. I don't have the multiplication of the two functions. But I would say to you, hey, you have. So you have ln of x and dx. So you can look to them as a separate functions here. So can you take the derivative of the ln of x? Well, yes, I can do it. So that is why I'm going to denote the u as the ln of x. And the rest, which is the dx, is going to be denoted as the dv. So the dv is going to be denoted as the x. So this is the u, and this is the dv. And if you look to this formula, I need v, and I also need the du. Du means that I need to take the derivative of the ln of x, which is 1 divided to the x, its derivative, right? 1 divided to the x times the dx, and dv is equal to the dx. I can get the v to be equal to the x. Then I'm just going to put all of these ingredients into the formula in order to evaluate this integration. So this integration is going to be equal to the u times the v, in this case x times the ln of x, minus the integration of the v du, so in this case x times the du, which is 1 over x dx. Well, you see, so everything is becoming so much easy now. So I'm going to take the integration of the 1, which is going to be simply equal to the x plus the constant. Well, you can always check your answers by taking the derivative from the answer. So derivative of this function, which I'm going to denote as the capital F, should be equal to this function, the small f. So let's do this one more time. So the derivative of the capital of x with respect to the x is going to be, so I need to use the multiplication rule. right? So it is going to be 1 times the ln of x plus x times the derivative of the ln of x is 1 over x minus the derivative of the x is 1. And you can see here that these two terms are going to be cancelled out, and you're going to simply have ln of x, which is the small f of x, inside your integration. So this is how and when we are going to use the integration by parts. Let's do one more exercise. So I think you're a little bit experienced now. I think you feel whether you have to use the integration by parts or other method, and also you probably know which substitution you need to use, right? So in this case, again, so you've got the multiplication of the two functions. You need to get one of them as a u, the second one as a dv. Okay, so I'm going to take the x in the square as a u. So let's take the u to be equal to the x in the square. Then dv is going to be equal to the e in the power of x dx. Okay, so don't forget about the dx. It is really important, as we've seen in the previous one, because dv can be simply dx, right? So then du is going to be equal to 2x dx. Then v is going to be equal to the e in the power of x. Then I'm just going to substitute everything into the integration, into the formula, and evaluate this integration. It is going to be uv, which is e in the power of x times the x in the square, minus the integration of v du, which is 2x times the e in the power of x dx. Well, so the question is, do you remember when we need to use the integration by parts? And the answer was, we need to use the integration by parts if you feel that you can get rid of one of the functions when you have the multiplication of the two functions, right? So here we use the integration by parts, but we couldn't get rid of the x in the square. But don't worry, we have to use one more time the integration by parts in order to get rid of this 2x as well. I'm going to use the integration by parts one more time. So in this case, the u is going to be equal to the 2x, then dv is going to be equal to the e in the power of x dx. Again, du is going to be equal simply to the 2 dx, because the derivative of the 2x is simply 2. And v is going to be equal to the e in the power of x again. And then this integration of the 2x e in the power of x dx is going to be equal to uv, which is 2x times the e in the power of x, minus the integration of the v du, which is e in the power of x times the 2 dx. We can easily integrate this. It is going to be 2x e in the power of x minus 2 e in the power of x, and you can just substitute a whole bunch of this thing into here in order to evaluate the integration. So this is how we need to apply the integration by parts, and how we need to evaluate the integrals using the integration by parts. Well, thank you very much for your attention. I hope that this was helpful for you.